All right, let's go ahead and get started this evening. First, I want to thank everybody for coming this evening. This has been a great, thank you. This has been a great series, but a difficult one to put together. So I also appreciate the patience. It's been 4 months since we had the last presentation. So again, thank you for your patience with us in getting this thing put together. I think it's been a great series, actually, just despite that. And what we've been talking about is this, or celebrating, is this year of the solar system that NASA has been celebrating for almost 2 years, a Martian year, if you will, which is actually, they call it a Martian year. And the idea is looking at how our understanding of the solar system has changed over time. We start off back in September with David Sobel talking about just how the way humans view the solar system, our relationship with it has changed. And then we've heard talks on the science of our understanding of the solar system has changed. And tonight we'll wrap up talking about Mars specifically. Pretty good talk. Mars has had a very successful history of exploration over the past 50 years. So I think it's a good note to end on. Just real quickly, remind you if you got a cell phone, either turn it off or just silence it or buzz. Either way, it's less distracting. If you have any teachers in the audience, we again have certificates for professional development out on the desk there out front. Don't forget to sign up if you didn't get an email from me about this presentation or haven't in the past, or if you're brand new tonight, right in the front door to coming in, when you come in on the left, at that table is a sign-in sheet. So put your email down there and we'll make sure we let you know about all our upcoming presentations. And of course, join us afterwards for the reception out in the lobby and a chance to meet Dr. Clifford. And I also want to mention, since we're talking about Mars and MSL tonight, LPI is going to host an MSL landing event on August 5th/6th because it's supposed to land at 10:30 Pacific time, p.m. So it's a pajama party. Because it'll be 12:30 a.m. August 6th Central Time. So we'll have some things going on. We'll be streaming NASA TV so everybody can see what's going on as it happens at JPL. I'm actually lucky I'll get to be at JPL. So it'll only be 10:30 for me. Okay, let's get this started. And I want to introduce our introducer tonight. It's Andy Chaikin, who's a good friend of LPI. He's a science journalist and an author. He's written some books you may have heard of. Man on the Moon, which I believe Tom Hanks' HBO series is based off of that book. The HBO series, A Man
From the Earth to the Moon.
From the Earth to the Moon. He wrote A Passion for Mars, and his most recent one is called Voices from the Moon, which is just interviews he did, years of interviews with the Apollo astronauts, and it's just pictures from Apollo with text describing the picture. Or no, they're quotes from the astronauts. It's a fabulous book. Check it out if you can. So, ladies and gentlemen, Andy Chaikin.
All right. Okay. Handheld. Good evening, and Andy, thank you for the introduction, and thank you for allowing me to crash this very nice party at the last minute. I was sort of a late addition to the program. I've been really enjoying teaming up with LPI to try and help spread the message to the public about planetary exploration and why it's so important to us and why we really have to keep doing it. And I know that to all of you that may seem like a no-brainer, but there are a lot of people out there that have their minds on other things besides exploration, and understandably so. We're living in a time when there's a lot of pressure on a lot of people. People are having trouble figuring out how to pay the rent and put their kids through school and keep food on the table, never mind wondering about what might lie on the satellites of Jupiter and Saturn, or whether there might be ice at the poles of Mercury. But I'd like to just take a couple of minutes to talk about why those things are important, even in these tough economic times. You know, for me personally, I was never to use a Carl Sagan double negative, I was never not aware of other planets. I grew up in love with the idea of going to other worlds. When I was 5 years old in 1961, these things were still science fiction. But, you know, it wasn't very long before pictures of the surface of Mars were coming in and showing up on TV, and astronauts were walking in space and getting ready to go to the moon. And when I was in high school, Mariner 9 became the first probe to orbit Mars and reveal an absolute geologic wonderland. At the same time, the Voyager missions to the outer planets were getting going, and those really flowered right after I got out of college. And as I was sort of making the transition from being a science guy to a science journalist. But I think that, aside from the wonders that exploration reveals to us, I think there is another message here about what exploration gives us. And it has to do with how it teaches us to think in a way that's different from what the culture tells us. And Mars is a great example, because if you look at the history of Mars exploration, for many, many years, people wondered whether Mars might be inhabited. Percival Lowell, at the turn of the last century, made quite a stir with his claims to see that he could see canals crisscrossing the deserts of Mars, and evidence of a race of Martians who were trying to get water from the poles to the deserts where they lived. And we conjured up this vision of a Mars that was sort of a sister planet to the Earth. And that sometimes that even seemed terrifying, as you probably know about Orson Welles scaring people half to death with his radio play about a Martian invasion called War of the Worlds. But then as time went on and we shifted into the modern era of astronomy with better instrumentation, it became clear that Mars was much more hostile than anybody thought. And in fact, there were no canals, just a lot of very mysterious dark splotches covering the bright deserts that seemed to change over the course of the Martian year. Then finally we sent spacecraft there. And the first images we got of Mars from spacecraft were a total shock, even to the scientists. Because instead of showing a world with mountains and maybe dried up ocean basins or something like that, it was a very moon-like Mars. It was a Mars that was just covered with craters. And the next two missions after that kind of reinforced that view. So by the time the 60s ended, people had pretty much written Mars off as a kind of uninteresting moon-like world. Now, flash forward to November of 1971. And Mariner 9 is about to go into orbit around Mars, the very first mission to orbit another planet. And actually, it's one of my favorite dates in space history, because on November 12th, 1971, the day before Mariner 9 went into orbit, they had a little symposium at Caltech. And on the stage at Caltech were some of the greatest thinkers about Mars that we had in our culture. We had geologist Bruce Murray, who was a team member on the very first missions to Mars and was one of the first geologists to study Mars as a geologic body. And then we had Carl Sagan, who all of you know that name. This was just as he was becoming the world stage figure that he later became. He was starting to go on The Tonight Show with Johnny Carson and talk about Mars and really becoming a popularizer. And then there were two other people. There was Arthur C. Clarke, author of 2001: A Space Odyssey, and Ray Bradbury. And Ray Bradbury, we just lost Ray day before yesterday. And I have to say that Ray spoke better than any other human being I can think of about why exploration matters. And he did so very eloquently at this symposium. And it was later published in a book called Mars and the Mind of Man. If you ever get a chance to see that book, it's pretty hard to find, but you might be able to pick up a used copy somewhere or in the library. I highly recommend it, because here is Bradbury with his passion soaring, talking about visions of us going not only to Mars, but way beyond to other stars. And, you know, in the 1970s, it still seemed like that stuff was on our agenda. We were looking forward to maybe sending humans to Mars in the 1980s. All of that changed as the budgetary picture changed, and Apollo ended. We started to pull back. We still had robotic missions, but nobody's been beyond low Earth orbit since 1972 when Apollo ended. Anyway, back to Mariner 9. Mariner 9 goes into orbit around Mars and reveals an incredibly different planet than the one everyone expected. Yes, there were craters, But there are also giant volcanoes, the biggest of which is 3 times the height of Mount Everest. And there's a canyon system that's a couple of 1,000 miles long. It's almost as long as the continental United States. And then the biggest surprise of all, as mariners circled Mars and began to peer down through a vanishing dust storm that had initially obscured the planet, as these details emerged, the most startling details were valleys, winding channels, some of them branching, just like river valleys on Earth. And that's indeed what they were. They were carved by running water billions of years ago. This on a planet which today is so hostile, the atmospheric pressure is only 7/1000ths of what it is here on Earth. Liquid water literally cannot exist on the surface of Mars. And yet here were signs that this was a very different planet billions of years ago, perhaps even one that was hospitable to life. So I think that Mars in particular, but exploration in general, has some things to teach us. And one of them is leave your hubris at the door. Because if you don't, the door is going to whack you pretty hard in the rear end. You're likely to, if you think you have it all figured out, you're probably wrong. Now, that's not something that Americans like to hear these days. We've got a culture that really wants to have everything figured out. We really kind of want things to be clean, black and white, you know. And exploration teaches us that when we get into that mode, we're missing the boat. And I'll just give you one other example of this that to me is really the ultimate, which is the Hubble telescope. A few years ago found, by studying the light from distant stars and galaxies, that the expansion of the universe is actually speeding up over cosmic history. This was an astounding result that no one expected, and it opened up a can of worms, the likes of which we have never seen before in science, because it means that one result means that there must be some force acting counter to gravity, which we have no idea what it is. We just call it dark energy. And then that plus another component called dark matter, which we also have no idea what it is, make up 95% of the universe. I mean, I've talked to professional astronomers who say that when they go to their classes and their students sit there and they say, wait a second, do you mean to say that 95% of the universe is stuff that we have no idea what it is? And all he can do is say, yeah, that's the size of it. So, you know, exploration is there to remind us that it's okay to be wrong, because that's how we learn. It's there to remind us that our job is not to have it all figured out in advance. Our job is to keep searching with an open heart and an open mind to all the data that comes our way. And maybe if we can learn that lesson, we can do a little bit better job down here of getting along and solving our differences. And I just want to close by saying that this is a very difficult time for solar system exploration in particular. Now, NASA has limited funds. Most people don't realize that NASA only gets half a penny of your tax dollar. It's an incredibly small amount of money for the return that we get from all of this exploration and all of the technological advances that come out of that, the fact that exploration is a magnet to young people to study science and math and engineering. And so when I hear that Congress is cutting back on funds for missions to explore the solar system, I feel sad, because I feel like we're throwing away our technological seed corn. And so I hope that all of you will take that idea and think about it as maybe a rallying cry to try and turn things around so that we don't have a situation like China had, where they built up a great exploratory fleet in hundreds of years ago, and then they turned away from exploration, and Europe basically took over that role around the time of the Renaissance. I think to remain great and to remain fully human, we have to keep exploring. Well, I'll get off my soapbox now and introduce our speaker, the main event that you came for. Stephen Clifford is a senior scientist here at LPI, And he came here in 1984 after getting an undergraduate degree at Windham College in Vermont and graduate degrees in physics and astronomy from the University of Massachusetts at Amherst. And he's going to talk tonight about discoveries from Mars over 50 years of robotic exploration. And one of his biggest interests is the water story on Mars. And as we talked about, Mars today is a world where liquid water cannot exist on the surface. And yet we see, the closer we look, we see more and more evidence that water has shaped the surface of Mars. So that raises some questions that have really been driving the exploration of Mars for many decades now. What happened to the water? How do you start out with that much water and end up like this? Is there a cautionary tale in there for us? And also, if there was that much water, is it possible that conditions could have given rise to life on Mars, maybe in the distant past? Or is it possible that even now, under the surface somewhere, there might be remnants of liquid water that would still support, maybe even in some limited way, the existence of bacterial life on Mars? Of course, Mars, I've always felt that Mars is plenty interesting even without the life question, but that's what people really latch onto, and NASA has understandably made that the focus of its exploration. But I think as you hear Steve's talk, you'll find out that Mars is an incredibly fascinating world with its own unique story to tell. Steve Clifford.
Andy, thank you. It's a pleasure to have the opportunity to speak with you tonight. As Andy said, I'm basically a Martian hydrologist. If you asked anybody in Mars science today to come up and give a talk discussing the discoveries and insights of the past 50 years, you'd get as many different perspectives as you had scientists. My particular focus happens to be on water. And as you may have gathered from the slide, there is some evidence that Mars may have been once a very much different planet than it is today. What we knew about Mars before we actually sent probes there was in some ways quite a lot. We knew that it had an atmosphere. Mars looked fuzzy. We saw clouds on the surface. We saw dust storms that would expand from being local storms to encompassing the entire planet. We knew that it had polar caps that grew in the fall, reached a maximum, and then shrank in the spring, but persisted throughout the year, at least a small remnant cap. We knew its mass. We knew that its mass was roughly 1/10 of the mass of the Earth, and that it had a diameter about half that of Earth. So as you would expect from those characteristics, the surface gravity on Mars is less than Earth, about 37%. Some people saw a lot more on Mars when they looked through the telescope. And Andy mentioned the works of Percival Lowell. I've got a quote that I'm going to show at the end of the talk that comes out of Percival Lowell's last book, which I happen to have a copy of. I was given this when I graduated, when I got my PhD by a friend. And it's called Mars is the Abode of Life. And in fact, it is the question of life on Mars that continues to motivate our investigations of Mars, much of our scientific interest in Mars. There are many other aspects of Mars that we find appealing, but the chief driver, even today, remains the question of life. We may no longer be looking for domed cities and canals, but at the very least, we're looking for microorganisms. And there is reason to believe that conditions conducive to the evolution, to the development of that kind of life may have occurred on early Mars. I mentioned the polar caps, again, telescopic observations. This is the Hubble telescope. I wish we had had technology like that 100 years ago, but even with the technology that was available at the time, we understood that Mars had seasonal polar caps which would cover the areas higher than about 50 degrees latitude in both hemispheres, and that during the summers, that larger cap would disappear but leave a remnant cap that was estimated to be on the order of about several hundred to as much as 1,000 kilometers in diameter. Again, from looking at Mars and the Earth, we see a lot of differences. Earth obviously has a lot more visible water, but there's actually a lot of reason to believe that Mars possesses a very substantial inventory of water as well, but stored chiefly underground. Because Mars orbits at a distance that's 50% greater than the Earth's distance from the sun, Mars is a lot colder. Mean annual temperatures at the equator are about 220 degrees Kelvin. In Fahrenheit, that's about minus 60-something or 70 degrees Fahrenheit. At the poles, it's colder still, on the order of about 154 degrees Kelvin, or almost minus 200 degrees Fahrenheit. So we're talking about a planet that today has a significantly different environment than what we see on the Earth. In terms of the history of exploration, Andy touched on a number of the key missions. This is a table showing the 41, some people count up to as many as 45 spacecraft that have gone to Mars. The problem is some of these missions involved a lander and an orbiter, and so people calculate the totals a little differently. But the missions that are highlighted in pink are the Russian missions, which you see are heavily biased towards the time period prior to 1975, actually 1973 and earlier. Russians sent their first spacecraft to Mars in 1960. We didn't get a spacecraft to Mars until 1965. Unfortunately, all of the missions prior to 1971 that the Russians sent were failures. Russia has had some really tough luck when it comes to exploring Mars. The US has also had its share of failures. If you look at the total number of spacecraft we've sent 20, and we've been successful with 70% of those missions. The Russians have sent 19, and they've been successful with 13% of those missions. ESA has one spacecraft in orbit, but actually it was sent along with a lander, the Beagle lander, and the Mars Express spacecraft, which was the orbiter. Beagle was lost upon descent, but the orbiter has actually been enormously successful and has returned a great deal of very important information. And I'll be talking about that in greater detail during the talk. And then the Japanese have sent one spacecraft which failed to achieve orbital insertion around Mars. And that is pretty much the history of robotic exploration. The missions that I'm going to focus on are primarily the ones that have happened since 1997, which is when sort of the golden era of Mars planetary exploration occurred. But as a preface to that, to show you what the knowledge base was that era built on, I'll show a few slides from the earlier missions that Andy discussed. Again, the very first successful mission to Mars was the Mariner 4 in 1965, and it was a flyby, as were virtually all of the missions prior to 1971. As Andy noted, the first images we got back from Mariner 4 and the Mariner 6 and 7, which followed it in 1969, were a bit depressing for those of us who had grown up on things like War of the Worlds and some of the Robert Heinlein and Arthur C. Clarke and Ray Bradbury stories about life on Mars. We didn't see the dome cities or the canals, but that work by Percival Lowell, the popularization of Mars as a planet that was potentially an abode for life, I think provided a lot of the motivation that stimulated our space program from that time on. And we see that in the types of missions that were flown to Mars following Mariner 4. Again, Mariner 6 and 7 returned images of the surface that for all the world looked identical to what we saw on the moon. One thing I would point out about all three of these missions is that the flybys occurred so that they were basically imaging the southern hemisphere. And that turns out to be very important because the southern hemisphere of Mars is very different from the northern hemisphere. Again, as Andy pointed out, Mariner 9 was the first spacecraft to actually go in orbit around Mars. And the views of Mars that it returned looked nothing like the impression that had been created by the earlier missions. Again, we saw this large volcano, actually a number of very large volcanoes, but the largest in the solar system, Olympus Mons, which has a basal area that would cover the state of Arizona, and you could drop the state of Rhode Island into the caldera at the top. Some might say that's not a bad place for the state of Rhode Island. But, also, Valles Marineris, the great equatorial canyon, which was actually named after Mariner 9 because that's the mission that discovered it. We had no clue. This is a canyon system that would stretch from Boston to Los Angeles, and it was completely invisible in terms of our telescopic observations, in terms of the photographs that were taken by the previous 3 flybys. In some places, it is as much as 500 kilometers wide and as much as 8 kilometers deep. The Grand Canyon would look like one of the minor tributaries to this canyon. So it's really an amazing feature. And again, the most surprising thing is the evidence for flowing water in the planet's ancient past. And we'll talk in more detail about that evidence in a little while. It was also the first really close-up look we had at the nature of the polar caps. This is the North Polar Cap, which has a diameter of about 1,000 kilometers, and the residual South Polar Cap. Now, the South Polar Cap is actually a complicated feature in that there's this area with residual ice on the surface that has a diameter of about 300 to 400 kilometers, but it's superimposed on a sequence of layered deposits. They're as much as 1,500 kilometers in diameter, in which we think below the surface is just as ice-rich as the residual cap at the center. It's just that the surface ice has been defrosted outside this central portion. And again, we'll take a closer look a little bit later on. This is a mosaic of several hundred Viking orbiter images. Mariner 9 flew in 1971. The Viking mission flew in 1976. And actually, it consisted of 2 orbiters with 2 landers, and it provided a revolution in our understanding of Mars. You see the great equatorial canyon here in considerable detail. You see some of the very large volcanoes on what's known as the Tharsis Bulge, a rise on the equatorial region of Mars, where 3 very, very large volcanoes are located. You also see evidence of the massive scale of fluvial erosion that has occurred on Mars. Right along here, at the eastern end of Valles Marineris, and several other places in the boundary between the southern highlands and the northern plains, you see these massive outflow channels. These are essentially dry riverbeds, but at a scale that dwarfs anything that has ever occurred on Earth that we have any geologic record of. And again, we'll look at those in closer detail. This is a close-up of the largest volcano in the solar system, which Andy mentioned is 3 times taller than Mount Everest. And it's a beautiful photograph. But the thing that I wanted to emphasize here is the fact that it's surrounded by these white clouds. We know from instruments that were on the Viking spacecraft what the temperature of the atmosphere was here. And we were also able to measure the concentration of water vapor, and we know that these are water ice clouds. So Mars does get clouds like the Earth. They're just not as frequent or abundant as we see in typical photographs of the Earth from space. And these are some much higher resolution views of the polar caps that were returned by Viking. And again, this is the North Polar layer deposits. You see that superimposed on the ice, or actually incised into the ice, are troughs, a spiral pattern of troughs. And the origin of this spiral pattern has been a mystery ever since they were first discovered by Mariner 9. There are some ideas that are beginning to gain traction now that relate it to the sort of combination of the low incidence angle of sunlight that the poles experience, enhancing the sublimation of ice. The ice surface has waves in it, and the equatorward facing waves receive more sunlight, and so they tend to sublime more ice than the poleward facing waves. And it's believed that this system, that kind of insulation, combined with the wind patterns in the North Polar region, together contribute to form this very unique spiral pattern. Also notice this huge chasma. This is called Chasma Boreal. It extends over a distance of about 500 kilometers and is several kilometers deep compared to the elevation of the polar cap on either side. Back in 1980, I proposed the idea that this chasma was formed by basal melting on Mars. You may be familiar with the fact that the thickness of the Antarctic ice sheet on Earth and the Greenland ice sheet is great enough that geothermal heating, the heat radiated by the decay of radioactive elements in the Earth's crust, is sufficient to raise the temperature at the base of those ice sheets to the melting point. There are places where are glaciers in other regions of the Earth, such as Iceland, where the same kind of heating takes place, and where large subsurface reservoirs of water develop. These can discharge catastrophically, an event called the Jökulhlaup by the people of Iceland. And I proposed that something very similar might have led to the development of Chasma Boreal. I was wrong. And we'll get into the evidence for that a little bit later. It turns out that, in fact, the polar caps of Mars may have once been at the melting point, but it hasn't been at any recent time. It probably occurred billions of years ago, and we'll discuss the geologic evidence for that pretty soon. I mentioned that these are troughs that are incised in the ice, and this is a close-up of one of those troughs, and you can see that there is a very clear indication of layering in the polar ice. And we think that this records a record of climate change that extends certainly over millions, tens of millions, and in the south polar layer deposits, perhaps even billions of years. The north polar layer deposits probably have a maximum age on the order of anywhere from 30 to maybe 50 million years. But the south polar layer deposits, there is evidence that some of the landforms associated with those deposits are on the order of 3 billion years or older. In both of the polar caps, in the central parts of the polar caps, we essentially see no evidence of cratering. Cratering is a technique we use to date the planetary surfaces. The more craters we see, the older that surface is. And we've tied it with some of the observations of the moon and the measurements of ages of those surfaces on the moon from the samples that were returned by the Apollo astronauts. And we've used some techniques to extrapolate that kind of dating technique to Mars. And it would argue, again, for the polar regions, at least in terms of the ice-covered parts of the polar regions, being very, very young, and the older defrosted areas around it being older. I mentioned the outflow channels. These are, again, massive features. This is a topographic map that was generated by a laser altimeter aboard a spacecraft called Mars Global Surveyor that flew around 1999, 2000. And it measured the height of the topography beneath the spacecraft to a very, very high density over the course of the mission. In fact, so dense that this is not actually a photograph. This is just a measurement, a depiction of the elevations that were measured by that laser altimeter. And you can see very, very clear evidence of the types of terrains, the geologic features, the main geologic features that we see in the visual images on Mars. This is that great equatorial canyon, Valles Marineris. You see that at its eastern end, you get a lot of disrupted crustal material and evidence of fluvial erosion that extends into the northern plains of Mars. The southern highlands of Mars, this is the region that was imaged by the first flybys, averages about 3 to 4 kilometers higher in elevation than the northern plains. The maximums of difference in the southern highlands and the northern plains is much larger. But on average, there is this very large elevation difference. So the northern third of the planet is actually much lower in elevation than the southern two-thirds. And in addition, you see far fewer craters in the northern plains, which suggests that it is considerably younger than the cratered southern highlands. But I want to, again, draw your attention to these massive outflow channels. And we've blown up on the right here just a very, very small portion of this area of fluvial activity. And you can again see that these are enormous channels. This is a bar of about 25 kilometer scale bar. So these are really massive features on the surface. These rivers, these outflow channels, are different from what we see on the Earth. On Earth, you usually see tributaries feeding a larger river. And that's how our largest rivers form. You don't see any tributaries associated with these outflow channels. Instead, what you see are areas of chaotic terrain, areas where the crust is all jumbled up. And you see evidence that water discharged from these areas. And that's precisely what we think happened. We think that there was a reservoir of water beneath the surface that broke out for some reason and inundated, eroded massive amounts of the Martian surface and eventually emptied into the northern plains. We think the thing that kept the water in the ground is permafrost, is frozen ground. Again, the mean annual surface temperatures on Mars are very, very cold. We think that at the time the outflow channels formed, which appears to have been about the middle of Martian geologic history, we've got some ideas as to what the heat flow was at that time from various types of models. And it suggests that the thickness of frozen ground at the time these channels formed was on the order of 1 to 3 kilometers. So you had a very substantial thickness of frozen ground that acted as a barrier, preventing the water from being discharged, the groundwater from being discharged to the surface. But let's say you had an impact that broke through that frozen ground, or you had some igneous activity, maybe a volcano, maybe a large igneous intrusion that melted the ice, or an earthquake that fractured the ground. Any of these things could have allowed the groundwater to discharge to the surface and form these very large catastrophic outflow channels. There is evidence in terms of the crater ages associated with these channels that they just weren't a one-time event, but were reactivated over the course of maybe 1 billion or 2 billion years of Martian geologic history. The key question here is, why did you have these reservoirs of groundwater stored in the highlands? Water wants to flow downhill. Mars was much warmer, at least internally, in the past. So why wasn't that water in the northern plains? Well, maybe it was. Why do we care about water? Because its abundance and distribution have important implications for understanding the evolution of the planet's surface, atmosphere, and climate. Its presence appears vital to the origin and continued survival of life, and it represents an invaluable in situ resource for sustaining future human explorers. This central theme of water on Mars and its central importance has been the prime driver of NASA's Mars exploration program, and in fact has also been adopted as the primary theme by the European Space Agency and the other spacefaring nations that are sending missions to Mars. So there are, again, many important reasons for trying to understand the water cycle and how water has evolved over the course of the planet's history. A primary driver of exploration being its relevance to the origin and continued survival of life. Now, estimates of the total inventory of water on Mars, based on some of the earliest Viking measurements back in 1976, they attempted to look at the amount of water or determine the amount of water that the planet had degassed over its history. And they came up with the surprising conclusion that the planet had a total inventory of water equal to a 7-meter deep layer averaged over its surface. The geologists looked at this figure and kind of scratched their heads, because looking at the outflow channels, you needed a whole bunch more water to erode that than just a 7-meter layer. But these atmospheric guys, they're bright guys. They knew about chemistry and physics and atmospheres, so the geologists sort of backed away for a while. But by the mid-1980s, the geologic evidence had become overwhelming for significant amounts of water on Mars. And basically, the amount of water required to produce all the erosion that we see on Mars, based on very conservative estimates, suggests that you need an inventory equivalent to a global layer 500 to 1,000 meters deep. averaged over the planet's surface. Now, of that amount, we currently see 1/1,000,000th of 1% in the Martian atmosphere. That's enough that if you were to condense all the water in the atmosphere onto the surface, it would form a layer about 10 microns thick. So not very much water at all. Now, 5% of this inventory is observable in the polar caps. We know what the dimensions of the polar caps are from the laser altimeter, from the visual images that we've gotten from spectrometers. We have some idea as to the composition. And from another device, another instrument, radar, that we have used to sound the subsurface to investigate the nature of Mars below the visible surface. And I'll be talking a lot more about that in just a little while. So where is the remaining 95% of water on Mars? Well, we think it lies in the subsurface, as both ground ice and groundwater. Now, I mentioned the history of Mars. This is a sort of a chart showing that history in terms of the age corresponding to the density, a certain density of craters on the surface. So where there are few or no craters on the surface, we've got a very, very young age. Where we see a very high density of craters on the surface, we see a very old age. Mars, like the other planets in the solar system, is believed to have formed about 4.6 billion years ago, and that's there is a certain density of craters that we would expect to see for surfaces that are preserved over that period of time. Actually, that's a density of craters that we don't see on Mars. The oldest that we can actually see in the geologic record goes back to about 4.1 billion years. So that first 500 million years of Martian geologic history has been either eroded or obliterated by subsequent impacts. But scientists divide the age of Mars, or the timeline for Mars, into three different epochs. The first one goes from 4.6 billion years ago up to about 3.7 billion years ago. And this is a period of intense bombardment in the solar system when there were very large bodies that were colliding with planetary surfaces, where we think virtually all of the large impact basins on Mars were formed. These are features that are 500 kilometers and larger. And Mars has some impact basins that are as large as 2,000 or 2,500 kilometers in diameter. So really, really big impact events. About 3.7 years ago, things appear to have changed. There appears to have been a transition, both in terms of the global climate and in terms of the intensity of bombardment. The debris in the solar system was beginning to be swept up by the planets, and so the cratering rate was going down. And there's this period from about 3.7 to about 3.1 or 3.2 billion years ago called the Hesperian, which represents sort of the middle part of Martian geologic history. The outflow channels formed in the period from about 3.5 to 2 billion years ago. That enters into the most recent period of Martian geologic history, which is called the Amazonian. So the Amazonian is the most recent. It extends from the present back to about 3.1 or so billion years ago. The Hesperian from about 3.1 to 3.7, and then the Noachian, the earliest period, going from 3.7 to 4.6. Now, over that time frame, I mentioned that the estimates for the inventory of water are based on the erosion associated with the outflow channels. So this is an inventory of water that existed middle way through the planet's history. There's actually reason to believe that the inventory of water much earlier in the planet's history was a lot bigger than what existed on the planet 2 or 3 billion years ago. And part of that reason why we think it was larger is that there are processes for the loss of water, UV photodisassociation of water molecules that breaks it into hydrogen gas and oxygen. Mars's weak gravity doesn't allow it to hold on to the hydrogen, and so that hydrogen escapes. The solar wind. On the Earth, the Earth's atmosphere and the Earth's surface is protected from the solar wind by a strong magnetic field. And there's evidence that we've obtained from from some of the missions that have occurred over the past 12 years that Mars once had fairly strong magnetic field that might have preserved its atmosphere in a similar way. But at some point, back during the Noachian, back during this first 500 million years of Martian geologic history, that magnetic field died. And that allowed the atmosphere to start eroded by the solar wind. Water may have also been lost because when it is in contact with rocks, there are chemical reactions that take place where the hydrogen from the water combines with the minerals in the rocks to form hydrated minerals. So water is consumed in this process, and this is a process that creates things like clays, otherwise known as phyllosilicates. And we have detected these spectrally on Mars in a number of different areas. But some would say that we have not detected them in a sufficient abundance to reconcile with the very large estimates of the amount of water on Mars. We'll talk about that again in a little bit in a little while here. Now we're going to talk about the evolution of the Martian hydrosphere. How did water evolve on early Mars? And we've got some good clues about that. And I'll also discuss the case for an early northern ocean. As Andy mentioned, Mariner 9 revealed these integrated networks of small valleys in the southern highlands, the southern heavily cratered 2/3 of the planet. So we're looking back at the earliest times in Martian geologic history. And the presence of these features, which on Earth result from precipitation, suggests that the earliest conditions on Mars were much different than what we see on Mars today. The atmospheric pressure today is less than 1%. The temperatures are far too cold to allow significant amounts of liquid water to flow across the surface. And yet we've got evidence of widespread fluvial dissection in the heaviest, most heavily cratered terrains on Mars. Now again, we're talking about these features occurring in the southern highlands, this lower 2/3 of the planet that has very high density of craters and has the large impact basins, Hellas, which is the largest impact basin in the solar system. There are places in the center where it's 9 kilometers deep, and again, over 2,000 kilometers in diameter. And then Argyre, which is about 1,100 kilometers in diameter, but has undergone a more complicated geologic history in its interior. Again, you see that the northern plains have very few craters and are much lower in elevation, this being the elevation scale bar, than the southern highlands. So we have this suggestion in the occurrence of the valley networks that the early Martian climate may have been much different, may have been much warmer and more Earth-like than what we see today on Mars. But there are also people who say that, no, that's not the case. There are ways of creating these valley networks that don't require a more massive atmosphere, a warm early climate. And we're going to talk about both of those. If atmospheric precipitation did occur on a global basis, if Mars did have an early greenhouse climate, it is a severe challenge because as Carl Sagan observed when the valley networks were first discovered by Mariner 9, you have to deal with the early sun paradox. And that paradox is that 4 billion years ago, the sun emitted 30% less energy than it does today. As a result, the planets, given similar atmospheric conditions, similar distances from the sun, would have been a lot colder. So how do you increase the temperature enough to allow liquid water, to allow rainfall to occur on Mars? And the solution that people have focused on is the possibility that Mars may have had a massive early greenhouse, that it may have had an atmosphere with a several bar pressure of CO2. But there's a problem. Even several bars of CO2, several times the Earth's atmospheric pressure, is not sufficient to raise temperatures above freezing when you've lowered the luminosity of the sun by 30%. So what do you do? And that is a problem that plagues us to the present. We had a meeting that discussed early Mars just 2 weeks ago, where for an entire week we debated this issue. And basically the conclusion by most of the atmospheric modelers is that we're missing something, that there's some minor constituent in the atmosphere that was able to close the gap and increase the temperatures. And that could have been methane, and it could have been a number of other trace gas constituents that would have provided enough warming to allow those temperatures to go above freezing. But right now, at the present time, there is not a theoretical model that allows us to get to those temperatures with any kind of early Martian atmospheric conditions that we've been able to conceive of. If you try putting more CO2 than several bars into the atmosphere, it begins to condense and form clouds, and then it's reflecting light, more light than it is trapping with the greenhouse effect. So the more CO2 you pump into the atmosphere, the cooler Mars actually becomes. So what's the other possibility? What if Mars 4 billion years ago was much like the Mars we see today? Cold, temperatures, again, on the order of minus 70 degrees Fahrenheit at the equator and much colder at higher latitudes. But perhaps water-rich in terms of the amount of water stored as ground ice and groundwater in the subsurface. One possibility is that these large impacts that were occurring during early Martian geologic history, they would have created enormous amounts of molten rock that would have sat there on the surface for perhaps tens of thousands of years, melting any ground ice that was in the surrounding vicinity and interacting with groundwater and forming very, very large hydrothermal systems. Now, these hydrothermal systems, in addition to releasing water to the atmosphere, would have heated that atmosphere. And the higher the temperature of the atmosphere, the more water it can hold. If you've got a supply in terms of hydrothermal springs and evaporation that's associated with hydrothermal systems that's supplying water to the atmosphere, and then you have the normal prevailing winds of Mars carrying that water-laden air to cooler areas where the cloud temperature, where the heated air begins to cool, then the amount of water it can carry is reduced, and the excess has to precipitate out. Close to the impact, where the temperature of the atmosphere was still warm, that may have occurred as rainfall. Further away, it may have occurred as snowfall. So we have the possibility that even under current climatic conditions on Mars, large impacts could have produced sort of microclimate or regional climate conditions that allowed the formation of the valley networks. Whatever the earliest climate of Mars was, we believe that Mars has had a climate very similar today since at least the beginning of the Hesperian, the end of the Noachian, this early transition from one epoch to another in Martian geologic history that occurred around 3.9 to 3.7 billion years ago. So we may have started off with a hydrologic cycle on Mars that was very similar to what we have on Earth, where you had precipitation. If the precipitation happened at a low enough rate, that precipitation infiltrated and was introduced and replenished the groundwater supply. Where the precipitation was heavier, it would have saturated the ground, and any additional precipitation would have resulted in runoff, forming things like the valley networks. So again, a very, very terrestrial kind of environment. But as the temperatures fell below freezing, a freezing front would have developed in the shallow subsurface of Mars that propagated downward with time. As Mars has evolved, the amount of radioactive material in its inside Mars, in the crust and in the mantle, has declined with time. And so the heat production in Mars has declined with time. But just like on Earth, if you dig deeper into the ground, the temperature increases, and it's from this decay of radioactive material. So the temperatures at depth heat up, and it's possible that the near surface, while it was at temperatures below freezing, at depths of maybe just a few hundred meters on early Mars, the temperature was above freezing, and liquid water still survived under a thickening layer of frozen ground. But as time went on, as billions of years went on, that heat flow declined, and that would have resulted in the deepening of the frozen region, the outer surface of Mars. And that acts as a cold trap for any water in the crust. When you leave the door of your freezer open, you see that a layer of frost develops around the freezer. Very same thing would have happened in the Martian crust. As the freezing front propagated deeper into the crust, any groundwater would have experienced a depletion as vapor was transported from the warmer depths to the colder subcryosphere region, the region where the advancing freezing front was propagating into. If Mars had a very large inventory of water, then at the present time on Mars, we may have a condition where we've got a several kilometer or more thickness of frozen ground in the shallow subsurface, and much deeper below that, extensive aquifers. Calculations suggest that Mars may retain some permeability down to a depth of as much as 26 kilometers beneath the surface. On the Earth, it's pretty much limited to 10 kilometers, but given the lower gravity of Mars, porosity can extend to greater depths and allow the greater circulation of groundwater. On the other hand, if the inventory of water on Mars was very small, it's possible that as this region of frozen ground expanded, all of the water got cold trapped up into the cryosphere, up into this region of frozen ground, and no groundwater survives on Mars today. The question of whether groundwater survives seems central to answering the question about whether life survives on Mars today, at least in the deep subsurface. It's very possible that in the early stages of Martian geologic and climatic evolution, that life could have evolved. And if it successfully adapted to a subterranean existence, and there is groundwater on the planet today, there's absolutely no reason to believe that it could not have survived to the present day. There are plenty of terrestrial organisms that if they were introduced into an environment like this would be happy as clams for as long as that environment existed. Okay, this is just a graph, again, showing the age of Mars in billions of years and showing how the internal heat flow has likely declined with time. And we see that the temperature inside of Mars, or the heat flux inside of Mars, was far greater in the planet's early history. Today on Mars, if the inventory of water is large, we expect that the thickness of frozen ground at the equator is somewhere on the order of 3 to 5 kilometers before you get to temperatures that are above freezing. The polar regions, because the surface temperature is much colder, the thickness of the cryosphere is expected to be much greater. Now, evidence for the presence of subsurface water and ice comes from the different kinds of crater morphologies that we see on Mars compared to places like the Moon. On the Moon, which we don't think has any significant inventory of ground ice, at least at temperate and lower latitudes on the Moon, or any groundwater, we see that the ejecta around large craters was essentially ballistically in place, like a giant explosion went off in the middle and just deposited dirt all around it. On Mars, many craters have a much different kind of ejecta morphology, something that looks very similar to what you'd get if you dropped a rock into a pan of mud. And we essentially think that that's what happened here, that these impacts occurred into a very water-rich target. And that created the kind of fluidized ejecta, the kind of flow patterns that we see around these Martian craters. Just another example of the same thing. In order for water to exist in the subsurface, it has to have some place to reside. And we think that the Martian crust, much like the Earth's crust, has had a very complicated evolution that has lots of porosity from rock that was fractured by the repeated impacts, sedimentary deposits, both aeolian, that is wind deposited, and also fluvial sediments, weathering products, the interaction of liquid water with rocks that produce things like clays, volcanic flows, which can be very porous, and crater ejecta. That all these things have created the pore space in the crust that has allowed this large reservoir of water to occur in the subsurface. And in these photographs, we see the processes that tectonics have occurred on Mars, much like they have on the Earth, these grobens, these pull-apart features, volcanism, impacts. Again, this is a rampart crater. This was an oblique impact from an impact that occurred at a high angle. And we see lots of evidence of layered sediments. I'm not going to talk about that. One of the really interesting things that became evident in the mid-1980s, this was after we had been looking at the Viking data for maybe 10 years, was a presentation by a graduate student at a small college, from a small college in California, a guy named Tim Parker. Tim had been working on the MX missile program, doing geologic characterization of the areas where these MX missile launchers were going to be sited in Utah and other places out in the West. And one of the areas that he was assigned for his geologic mapping was a place that had hosted a very, very large lake back about 10,000 years ago. This was called Lake Bonneville. The remnant of Lake Bonneville is the Great Salt Lake. But Lake Bonneville was probably 50 times larger than the Great Salt Lake is now. So it was a huge body of water. And the record of its existence is expressed in the landscape with paleo shorelines, places where waves once cut sort of a bathtub ring around the basin that this lake inhabited. And again, Tim had walked all over this area, so he was very familiar with these features. And as he looked at the Viking orbiter images, he began to see things that looked similar to what he had seen in the Lake Bonneville area. And as he started to map the occurrence of these features, he found that they formed an outline around the northern plains. And his conclusion was that Mars must have once had an ocean. Well, when Tim presented this, everybody rolled their eyes. Nobody believed him. But Tim soldiered on, and he continued to do the mapping, he continued to look at the geologic evidence, and slowly, very slowly, he began to gain some converts. And in fact, today, there is very strong evidence, advocated by some and completely rejected by others, that Mars once hosted an ocean that covered more than a third of its land area, a third of its surface area. And in addition, it may have also had very large seas in those large impact basins, Hellas and Argyre. I came about to a similar conclusion by a very circuitous route. And that was, again, by considering this question of how you get water at high elevations in the middle of Martian geologic history that then dumps and forms the outflow channels. If Mars had been warmer in the past, as we think it was, the geothermal output was much higher, even if the surface temperature wasn't. The thickness of the cryosphere, the thickness of frozen ground would have been too thin to preserve any high elevation reservoirs of groundwater. The groundwater would have provided enough hydraulic pressure that water should have broken through the cryosphere and flooded the various lowest regions on the planet. And it was in thinking about this that I came to the conclusion that if Mars actually did have an inventory of water that was a half kilometer to a kilometer in scale, then earlier in the planet's history, it must have had an ocean. There's simply no way you could have maintained that disequilibrium of liquid water and